Just like we talked about selection rules for other kinds of spectroscopy, for example, rotation and vibrational spectroscopy, we're going to introduce selection rules here for electronic spectroscopy. Recall that when we talked about a single electron atom, we introduced the selection rule delta L. The change in the orbital angular momentum quantum number would be plus or minus 1, and the change in the m sub L quantum number would be 0 or plus or minus 1. Then what we did was introduced spin-orbit coupling, or Russell-Saunders coupling, or LS coupling, three different names for the same thing. And in that case, we said, oh, the orbital and intrinsic spin couple to give a new set of quantum numbers, and these new set of quantum numbers are S, L, and J. So we go from there to there with LS coupling, and now we're going to introduce a set of selection rules for these new quantum numbers. That's what's on this slide. Delta S, that's the total spin, intrinsic spin quantum number, that has to be 0. So for example, you cannot have a allowed transition between a singlet and a triplet state because delta S there would change, wouldn't be 0. Delta L is 0 or plus or minus 1. Note that's a little different from this where delta L was plus or minus 1 without LS coupling. And then delta J can be 0 or plus or minus 1, except that the J going from a 0 to 0 total spin angular momentum is forbidden. So with these selection rules and with our previous discussion about the electronic states, the electronic ground states of carbon, let's see what sort of transitions we can have. So this is the ground state of carbon. And recall that we had 5 states in the ground state. It's kind of weird, but yes. So we can have even without going to an excited state. And recall that what we're defining here by ground state means n equal 1 for the 1s electrons and n equal 2 for the 2s and the 2p, 2 and the 2p. So that's what I mean. We're not changing the principal quantum number n. But within this set of states here, actually the p orbitals, we have different electronic states, and we can look at transitions between them. So recall that the ground state was a triplet p0. This is a triplet p1. This is a triplet p2. And then the next higher level we found experimentally, D2, and then we had the singlet S0. So let's use the selection rules. Delta S equals 0, delta L equals 0 or plus or minus 1, and delta J is equal to 0 or plus or minus 1, except a 0, 0 transition. Delta S equals 0 means that we can have transitions within this triplet manifold here, or we can have transitions between the singlet manifold, but we can't go from a triplet to a singlet. So we're governed just by this. And we know delta L has to be 0 or plus or minus 1. So from that, we can go to any one of these. However, delta J has to be 0 or plus or minus 1. So that means the only allowed transitions in this triplet manifold will be from there to there. Actually, it could be emission or absorption. Here, delta J changes by 1. You can't have a 0 to 2 transition, so this transition is not allowed. And we can also have this, where we go from the triplet P1 to the triplet P2. So those are the only 2 transitions within this triplet manifold. Now we go up here. Let's see if this is allowed. Well, no, that's not allowed, because here delta J would change by 2. It's a triplet, that's allowed, but delta J changes by 2, and L changes by 2. This is L equal 2, L equals 0, so those are not allowed. So of the allowed transitions, only 2 are allowed here. These are allowed transitions. by the selection rules here. And I put allowed in quotes because, as we know, our quantum mechanics is not perfect here. We've made some assumptions. So there are also some forbidden transitions. You could see some forbidden transitions here. That's selection rules for electronic spectroscopy in the case where you coupled intrinsic spin and angular momentum spin to get the quantum numbers capital S and capital L, and then you couple those to get capital J.